Introduction. No, okay, in all seriousness, Jonathan Kade is going to be our main presenter. Let's say I'm in the blue shift. Am I blue? All right.
You're blue.
Jonathan Kade will be presenting on the end of the universe. I think it's going to be pretty interesting. For those of you who have been living in a gutter the last 6 years of your life, Jonathan Kade is a former president of the Warren Astronomical Society. He's held some other positions, we don't need to go into that, but he is our merchandise man, our librarian, our astronomical league coordinator. He's trying to get rid of maps, but webmaster.
Librarian?
I said librarian.
Okay.
He also,
Merch?
I said merch.
Calendar designer.
Calendar. He also does the credit card purchasing. He is a man with many hats. He's trying to get rid of them. No one will take them, so he continues to wear them, and we greatly appreciate that. Jonathan Kade, everyone.
And if you would like any of those jobs. Good evening. So we're here to talk about fun things. Basically, 2 years ago, I think in October, I gave a presentation on the beginning of the universe as we know it, about the Big Bang Theory, about competing theories to the Big Bang Theory, and why the Big Bang Theory, specifically the lambda cold dark matter Big Bang Theory, is still the dominant theory. So we'll touch a little bit on that, but I figured if I covered the early parts, I should cover the late parts too. So
Is Tired Light going to make an appearance?
if Tired Light makes an appearance, it's somebody else's fault. So, all right. So here's a brief overview of what we're going to talk about. So first, we're going to talk about what kind of universe we live in, and then we'll talk about some of the four big titans in the end of the world stakes, and then we'll talk about how we might be able to test them. So I wanted to give a brief shout out at the beginning of this to a book that got me started down the path of being interested in this. I think it came out in 1998, and I was having a very bad day when I started reading it, and reading about everything going away made my day a lot better. So that was probably the first grown-up astronomy, astrophysics, cosmology book that I read. And it's written for a popular audience. It's a little bit out of date now. I don't think Timothy Ferris, who also wrote Coming of Age in the Milky Way and Seeing in the Dark, has updated it since then. But it's still a great read, and I'm not aware of any book that really takes on the same the same purposes that is more recent. So this goes out to him. So the first thing we're going to talk about is what kind of universe it is.
Too bright. The complaint was it's too bright.
That was the Big Bang. So to figure out where the universe is going to end up, we need to have some kind of understanding of how it got rolling in the first place. We need to know sort of what kind of universe we live in now. So is the universe that we live in now expanding? Is the rate at which it's expanding accelerating, constant, or slowing down? And what about inflation? So you may recall this beautiful graphic from the WMAP team. So basically, we have some uncertain point before the Big Bang that goes down to the 10 to the minus. We don't really know anything that happened before 10 to the minus 40 seconds after the Big Bang. But everything since then we know to some degree of certainty. So we have this afterglow light pattern, which is the cosmic microwave background radiation that we see when we look at the universe in radio frequencies. we had the dark ages where everything was so dense that photons couldn't get around. And then we had stars emerge from the plasma muck, and that's been happening ever since. And we think that we have an accelerated expansion, and so that's going to be a major topic of the presentation tonight. So, what is the Big Bang? So, the singularity, the Planck epoch, is when all of the forces, all of the fundamental forces we have now were unified. So, gravity, the strong and weak nuclear force, and the electromagnetic force were all one big happy force together. And then gravity breaks off in the grand unification epoch. The electromagnetism and the weak nuclear force are unified for another fraction of a second, and then inflation has been added in since then to explain how the universe got as big as it is now in the amount of time that we think it's been around. Then we started forming particles and nuclei during that dark age, and went into the recombination era and the plasma era, and then stars emerged, and that has been to 100 million years after the Big Bang to the present day, which is about 14 billion years. So, you may recall that one of the major stories in our discussion of the Big Bang, if you were here 2 years ago, or if you've read about it, is that Albert Einstein, when he was putting together his theory of general relativity, he first published his theory of general relativity in 1914, and he just kept cranking out paper after paper developing it. And one thing that was pointed out to him very early on after he published the theory of general relativity is that the universe that his equations sort of produced was extremely unstable and could collapse or expand. And to a world and to a scientist who were very enmeshed in the idea that the universe was in steady state, it wasn't changing, it was very stable, this was a very big problem. So he added in this lambda here, which became known as the cosmological constant. And so he added this term here to try to produce a stable universe that would be compatible with the steady state universe where nothing changes very much. You know, it might expand a little bit, but it is fundamentally, you know, not really changing significantly. So Einstein called it his greatest blunder, I think, to George Gamow. Putting that term in and not realizing the significance of it. So the problem, so he was kind of far-seeing because that little lambda turns into something pretty significant to modern physics. But in terms of making the universe actually stable, it doesn't do a very good job. So I'm going to talk very briefly about this equation here. So these are all tensor math. So this is basically four-dimensional. Each of these components here are in 4 dimensions. So he was going for 3 dimensions plus time in modern, you know, string theory and the more complex mathematical models of the universe. There are much higher order tensors, but this is still, I still have not been able to wrap my brain around everything. But the G term here is Newton's gravitational constant. C is the speed of light in a vacuum. And this tensor basically is the relationship between stress and energy. So basically how space-time holds together. And so And this lambda here is, this is called the metric tensor. So basically, his cosmological constant is this sort of, it basically gives a little push in every dimension of the equations to try to stabilize it, to control the behavior of the system. So a lot of people think that the first person to talk about an expanding universe in a serious way was Georges Lemaitre, who was the Belgian physicist and priest who sort of proposed the Big Bang in the first place. That's not exactly correct. So Alexander Friedman, who is a Russian/Soviet physicist, introduced an idea of an expanding universe only 8 years after Einstein had introduced the idea of general relativity. Both he and Lemaitre were completely obsessed with general relativity and published many papers on it. So in 1922 he starts talking at symposiums about the possibility that Einstein's general relativity universe could be expanding. Not really thinking about Big Bangs, not really thinking about the origins of the universe, but talking about just the universe that we live in today. And so in 1925 he publishes a paper about the possibility of living in a universe with a negative curvature of space, meaning that it's expanding. So the FLRU equations are named the Friedman, Lemaitre, Robertson, Walker metric. So Friedman, Georges Lemaitre, and Robertson and Walker all separately developed usable versions of Einstein's field equations. But the people talk about Friedman equations specifically. So the Friedman equations basically determine the fate of the universe. So you may recall that in the 1930s, Edmund Hubble discovered a relationship between the distance of standard types of stars and how fast they were moving away. And so this component on the left side here ends up being the Hubble constant. And so that lambda that Einstein introduced pretty much turns into the Hubble constant, where basically it's composed of different types of mass densities. So basically, when you think about the universe being composed of, all of the stuff in the universe, you have matter being this term here, this omega of m. So matter is regular intergalactic gas, stars, and dark matter. Oops. You have the radiant mass density, which is neutrinos and photons and other quanta of radiation, other things moving through space, and that's pretty negligible. And then you have the cosmological constant, the Hubble. So basically, this is Einstein's blunder here, and that's a fundamental part of the Hubble constant. So the question is this actually constant? So dark energy is, so Einstein's lambda is dark energy. So when people talk about dark energy, it's the cosmological constant that seems to be pushing the universe out. So what these three types of mass density add up to has a big impact on the type of universe that we live in. If we live in a closed universe where space is curved essentially in on itself, you have this omega constant being greater than 1. If the omega constant is less than 1, you have space negatively curved and stretching out. And if you have an omega of 1, then you have a totally flat universe. These are from W.A.S. too. So Yep, so it's dark energy time. So what do these mean to the future? If you have a closed universe where expansion is sort of limited and you are going to start closing in again, you arrive at one destination. If the curvature is open, you arrive at another destination, and if it's flat, then you arrive at the best destination of all. So we're going to start from the closed universe approach, the big crunch. So here's another way of looking at the same thing. So here we have our omega values here. So a flat line produces a linear outcome. So if basically the curvature of the line, if you're going to, if you have a value over 1, it's always going to collapse. If you have a value that is less than 1, it's always going to expand. So in the big crunch, basically you have a Big Bang starting at the beginning, and you expand out, but this curvature has some kind of finite end to it. And so basically you reach a limit at which the this mass density of the universe overcomes the underlying space-time, and everything starts pulling back in, and eventually you get back down into a singularity. What's nice about this model is that it sort of makes an intuitive degree of sense. Like if you have a Big Bang, then it kind of feels good to have it crunch together and then have another Big Bang and then crunch together. And so, you know, it's unfortunately probably one of the less likely possibilities. So basically, so here's the open universe and the closed universe. So this is sort of an artist's conception. So that's the big crunch. So space-time expands to a certain extent. It hits some natural limit that is determined by the properties of space-time, and then it collapses back in on itself. The big rip is the case where basically expansion accelerates and becomes unbounded and heads for the ceiling. So in the big rip, you have one start in the Big Bang, and then the universe continually expands forever. And so the idea of expanding forever and an accelerating expansion has basically the expansion of space-time overpowers gravity. So it overpowers gravity, and then it overpowers the electromagnetic force, and then the weak nuclear force, and then the strong nuclear force. And so basically, space-time gets stretched so far out that first large-scale structure like galaxies, first you get galaxy clusters disappear from each other. So we're in the local group. We're part of the Virgo supercluster. But all of the other clusters of galaxies, all these pretty galaxies that we see around us, become so far distant from us that the light from them can no longer catch up with us. So they leave the visible universe. And in a big rip universe with accelerating expansion, that starts affecting even things like galaxies themselves. So first you get the galaxy clusters pulled apart so that you can't see from one galaxy cluster to another. Then you get the galaxies themselves, the space that the galaxies are in has expanded so far apart that gravity no longer holds them together. Then as you get closer and closer to the moment of the big rip, even small, and so these are, I'll talk about that in a second, the even small scale structure like a solar system, you wouldn't be able to see, from Pluto to Earth anymore. The space-time between them would be so large that photons coming from Pluto could no longer make it to Earth before Earth was, Earth is moving away from Pluto faster than the photons can get there. And then, so this says Earth explodes. Obviously, this is going to be very, very far into the future. Our solar system won't be around by then anyway, but things like our solar system. And then finally, right as the big rip happens, atoms start getting ripped apart. So this also is not the most likely outcome, but it's definitely probably the most exciting. So the big freeze is the current reigning most plausible theory. The big freeze holds that we are in a totally flat universe and that everything is just simply going to expand forever. So depending on the circumstances of it, so expand forever but expand at a constant rate rather than an accelerating rate. So what that means is that superclusters, the large-scale galactic structure, will still become inaccessible to us. So we will still lose track of other superclusters. We won't be able to see all these galaxies in the Hubble Deep Field or Ultra Deep Field anymore. But the Milky Way will continue to be a galaxy. Our local group will, all of the galaxies in our cluster will form a cluster together, and for a long time we'll stay more or less together. So even in this model though, where you don't have space-time completely ripping apart from under you, you still have the problem that time is moving forward. You're losing the energy. Basically, energy can neither be created nor destroyed, but the organization of stuff, the structure that was created in the immediate aftermath of the Big Bang that formed galaxy, I wish I had a picture of it, but the large-scale structure of the universe, all of the chains of superclusters of galaxies. Basically, at every scale of the universe, you have some kind of structure. And if you look at the arrangement of large-scale galaxy clusters, it looks kind of like a spider web in space. So that structure all was formed by some mechanism. I think symmetry breaking is credited with there being a universe of something instead of nothing. Basically, in the immediate aftermath of the Big Bang, there was more matter than antimatter. But all of the all of the potential energy that was in whatever was before the Big Bang has been spreading out through an infinitely expanding volume of space-time. And so we know that our sun is going to die in a matter of a few billion years. We know that the universe is expanding. And we've even seen in some other galaxies the results of galaxies running out of fuel. So if you look at M82, the cigar galaxy, you see it has passed too close to the very large M81 Bode's galaxy, and most of the fuel for making stars in that galaxy has been turned into stars. When those stars die, that galaxy doesn't have enough fuel to form any new stars. So if you take that principle and expand it over huge volumes of space and huge quantities of time, what you get is all of the brighter stars in the universe finally dying out, and the concentration of mass in every corner of the universe becomes so spread out that you can no longer form new stars. In that future, we end up with a few things left over. So at 1 trillion years from now, well, 1 trillion years from the Big Bang, you can no longer see the cosmic microwave background radiation. It will be outside of the observable universe for everybody. And 10 trillion years from now, the red dwarfs, which will have been burning on almost eternally, will finally turn into blue dwarfs. So, and then when the blue dwarfs finally burn out on the 100 trillion year time scale, the only thing that will be left is black holes. And black holes will be the only thing radiating into the universe. And black holes will be radiating via Hawking radiation, which is a very dark kind of radiation. So it will be a very dark place. So this is not an artist's conception of the Big Freeze. I tend to say the Big Chill instead of the Big Freeze. So this is an artist's conception of the Big Chill, the Big Freeze.
Did you make that?
I did. This is my artistry. So I'm guessing most of you have heard of the previous three models for the end of the universe before, but vacuum collapse is a fairly new one, and it's an exciting one because it really doesn't deal with the properties of dark energy and the properties of the general relativistic universe. Instead, it has to do. Instead, it has to do with a particle that you've heard a lot about in the last few years. So, basically, the idea with vacuum collapse is that space-time is constrained by the existence of a vacuum, which is kind of an interesting mental challenge. But vacuums can have certain properties. So basically, this equation. So the idea of this vacuum comes from fluid physics. So they took pressure and density equations from fluid physics and expanded it to the universe at large. And actually this does sort of tie into dark energy. I was a little bit wrong. So P is pressure and rho is the energy or mass density. And so that sort of is what determines the type of vacuum that you're in. So if you're in an unstable vacuum, then you're rolling down this hill. So essentially, you basically structure, when you're unstable, structure doesn't really hold together. The properties of everything are changing, and the rules of the universe are going to change on you. But what's dangerous is that you get into a metastable point. So if you're in a true vacuum, you can't go back up the hill. You are at a totally stable point as far as the ground rules of the space-time that you're in. And you can't actually, nothing can really disrupt that. But if you're in a metastable point, which is like a little trough, imagine you're this boulder rolling down a hill, and you end up in this little gully on the side of the hill. If some event should push you over this lip here, then you're going to fall down into the true vacuum. You're going to be at a stable equilibrium. But as long as nothing pushes you too hard up here, you're okay. So the vacuum collapse or false vacuum, so this is a true vacuum, this is a false vacuum, or a metastable vacuum. So the idea here is that we could, unbeknownst to us, be in a universe whose ground rules are set by some kind of false vacuum. And it could be that some extremely high energy event could push some little corner of space-time over the hill out of metastability back into instability that would then, after some long drawn-out process that would instantaneously destroy the universe, end up in true stability. So this is one of the reasons a lot of people got freaked out by the Large Hadron Collider because of the idea that perhaps people might produce a black hole on Earth, a micro black hole on Earth. But some people got freaked out because of the idea that doing high energy physics could potentially destabilize the vacuum that we're in. To which people working at CERN, working at CERN said, have you ever heard of neutron star collisions? Basically, the actual high energy things that happen in the universe are so much higher energy than anything that we can possibly do on Earth that it's not a very realistic concern to have about the LHC. But it is an interesting thing in the universe at large. Like if you have certain properties, actually for some reason there's a lot of research going into micro black holes and how they could potentially destabilize the space-time vacuum. So I'll talk about that. So this is an artist's conception. I don't know if anyone saw this movie. I didn't actually see this movie, but it's from the Marvel Infinity War movie. So that was Spider-Man evaporating. So basically, the only way you'll know that you were in a false vacuum is when it collapses and you cease to exist. So it's not so much a rude awakening as it's anyway, so how do we test these theories? How do we figure out what the future holds for us? Well, this diagram actually does a pretty good job of giving you an idea of what we might be able to figure out. So we are here, and we want to know where we're going in the future. So the only way we can really figure that out is to see what has happened before. If we look at, so basically, if we look back in time using our new observatories that are coming online, do we see that the rate of expansion going back fits this curve better, or does it fit this curve better, or does it fit a straight line better? So, and another interesting aspect is that, so you have these two decelerating universes. So this decelerating universe and this coasting universe both produce the big chill. If you have a decelerating universe that is decelerating at a faster, like if you decelerate to zero expansion, you sort of eventually turn into a coasting universe. Like if the Hubble constant is actually a constant, then it produces this universe. But if the Hubble constant slowly gets to 1, then you end up with this universe. If it ends up under 1, you collapse in on yourself, sorry, over 1. And if it is under 1, and then you end up ripping apart. But from our present day, these different theories actually make different predictions about how old the universe is. So if we can figure out with a degree of certainty how the expansion that we see through recorded through astrophysically recorded time, if we can figure out which curve is closest to what we observe when we look at more and more and more distant galaxies, then we can figure out with a certain degree of certainty how close to the critical values we are. So one of the tools that we are going to be looking to perform this is the James Webb Space Telescope, which I think now is supposed to launch in 2021. The Webb is going to be equipped to look further back into the history of the universe than any human-built device has ever been. So it's not going to push us back to the Big Bang, but we're going to get closer and closer to the Big Bang. So that is a very expensive device that we hope will help us figure out with certainty which kind of universe we're living in. And also, I alluded to this earlier, so the Higgs boson was detected at CERN a few years ago in the Large Hadron Collider. So it turns out that the vacuum collapse of the universe has a lot to do with the nature of mass, and the Higgs boson is the fundamental particle that conveys mass to stuff. So it turns out that the mass of the Higgs boson and also the mass of the top quark together basically determine what this curve looks like for our universe. So right now, with the tetatron plus the Large Hadron Collider, we've reduced the degree of uncertainty about the mass of the Higgs boson to this outer ring here. With planned enhancements to the Large Hadron Collider, we should be able to figure out to this degree of certainty. So basically, with enhancements that are being made right now to the Large Hadron Collider, we can rule out the possibility that our space-time is in an unstable vacuum. We still won't be able to figure out if we're in a metastable vacuum where we could get pushed off into oblivion, or whether we're truly in a stable vacuum. So hopefully, so the ILC is the International Linear Collider. It is at this point somewhat funded, but not completely. It's a collaboration between Fermilab and CERN. And so this is the size of a soccer field. And so you've got damping rings and then a very long 31-kilometer linear accelerator with which they hope to get the uncertainty about the masses of the top quark and the Higgs boson down into a range that we could say it's either metastable or stable. So the arrangements of these rings of certainty are guesses at this point. Like we don't know where these really are. So it's going to be exciting. So between the James Webb Space Telescope and the ILC, if it is built, or maybe as the LHC is enhanced, we might be able to start ruling out some of these potential ends to our universe. And obviously, for us, even though it's sad that in the Big Freeze, basically atoms cool down so much that they can't hold together anymore, everything turns into, in the words of the author Thomas Pynchon, a gray salad of despair. But you basically have just you just have a coating of dust across the entire universe. All the knowledge that humankind has ever gained, all the books ever written, all of the works of art, everything is just reduced down to little partial particles. And it's sad, but it's also a lot slower and a lot less painful than a big rip or a quick collapse or everything simply popping out of existence. So right now, the Big Freeze hypothesis matches what we have measured of the Hubble constant the best, and hopefully we'll be able to increase the certainty of that. And so pretty much the only way that we're going to know for sure is to get there, and I'll be happy if we, as a species, last another 1,000 years myself. So anyway, I have a whole bunch of resources here. There's some really cool papers. Some of them are scientific papers that I was only able to understand small pieces of, and some of them are popular papers that are quite readable. So, that said, are there any questions?
So I noticed that Friedman's big paper on a negative curvature was 25, and he died at that year in the Soviet Union. Is there a story there?
So Friedman died at 37 years old. He's one of these, along with Jeremiah Horrocks, he's one of these people who were extinguished well before the time at which they might have made their best contributions. But nevertheless, he made extremely significant contributions, and his practical. So Einstein was a hard to follow mathematician. So Friedman and Lemaitre made it much easier for people to work with the general relativistic framework, and so it's it's hard to say. Some would say that Einstein's best work did not really last for much longer than when he was at a similar age. So who really knows what the future holds? But you asked if there was a story behind the fact that he died at 37, which is how old I am. So he actually had just married his second wife, and he went on vacation in Crimea, and he contracted typhoid fever on his honeymoon, and he died. So he actually, he was untouched. He was very well liked by the revolution, by the Bolshevik revolutionary leaders. He didn't have any problems with them, and he actually ended up, working with them. I don't know how committed to, the Bolshevik cause he was, but he certainly didn't have any problems with them. So. Any other questions? Yes, Brian.
Yes. Right now, the cosmic microwave background radiation is what, about 2.7 degrees Kelvin? You would know this.
So the overall temperature of I think the average temperature of the universe is like 3 degrees Kelvin, or 3 Kelvin.
Yeah, something like that. Now, if you were to go back.
But the big freeze the big freeze is called the big freeze because you reach 0 Kelvin. So basically, that's the Kelvin scale is the scale meant for dealing with this. So Kelvin doesn't have degrees. Kelvin just has units. So when you hit 0 Kelvin, nothing can hold together. Everything just sort of, everything stops moving. You no longer can have any kind of atomic processes. You can't have chemistry. It just.
So if you were to go back in time a billion years, it'd be a little bit warmer.
Mhm.
And if you were to go ahead, a billion years, it'd be a little bit cooler.
Yes.
Not a lot, but measurably so.
Right. Yeah, I mean, 3 Kelvin is really cold, but it will get colder still if the big freeze is indeed what the future holds for us.
Well, I read somewhere that it'll approach 0, but it'll never get there.
Yeah, that's true, but eventually when you can no longer have anything happening in the universe, when you have 100% entropy, it really doesn't matter if you truly get to 0 Kelvin. Jeff, did you have
Yeah, I was just wondering if you, in researching this, came across any credence to like phase transition type theories. This going from unstable to stable vacuum kind of sounds like that kind of phase transition.
Is this like brain?
The analogy I heard was like, think of inflation as a phase transition between
okay.
like a
Yeah, and
hypothetical-
actually, so this, to go all the way back to the beginning,
the very beginning.
oh, that's not bad. Yeah. That's the right slide, come on, really? So this graph, unlike the other ones, actually shows inflation happening.
Yeah.
So you could have, yeah, well, I mean, so the big crunch, so the thing is, if you look at this particular curve, now obviously, depending on what omega is, we could be at any point on this curve. But we know that we are not here because as far as we can tell, the universe is still expanding. If we were here on the curve, we would see blue shifts everywhere. Everything would be getting closer to us. And I just realized 3 of my slides didn't show up in this, so I wonder where they went. So this would be sort of now it's true that like no one knows what the actual mechanism of inflation was. That's one of the reasons people hate inflation so much is that it doesn't have a mechanism for it. It's something like the math fits what we observe in the universe today very well, but no one has any idea of what would make space-time inflate.
It's a neutrino.
Yeah, so there's actually a proposed particle called an inflaton.
No.
That was some transient particle that caused inflation. So that's like that's sort of like black swan
I just wasn't
sort
sure
of
if
stuff.
maybe
So of course we only know. We keep learning new questions to ask, but and there are other things like if you get into brain theory or string theory, there are certain predictions that they make, like I think like brains colliding with each other could cause,
Right.
but I generally try to stay as far away from brain theory as I can. So.
Yeah. I was just curious if maybe you came across something that was like it's complete bunk. It's just an idea that was proposed with really no substantial claims to why you would. Because I've heard I think it was Max Tegmark, saying it could be in as little as 1 billion years, which is you better stock.
Was he talking about a false vacuum?
I didn't hear false vacuum, but the analogy he was making, if I have the correct Swedish scientist,
Yeah.
that he compared it to like a phase transition where you have certain physics and then magic happens and you have different physics. And
Yeah, and so having, we know, based on what we have observed based on what we've observed in the universe up till now and used to make predictions, like the Hubble constant, quote unquote, is made up of different things, but maybe there are other things that we don't know about.
Yeah.
There's just, you don't know what you don't know.
Right.
But I came across a fair amount of Tegmark's work in researching this, and I don't remember seeing anything that really stood out to me, so I'll have to look into that.
Maybe he might be the wrong guy. I know he's a simulationist, but
Were there any other questions? So, Jerry, is there anything that I got egregiously wrong?
Well, I don't know, this is very esoteric stuff, I don't understand that very well myself.
Okay, that's a relief. Cool. All right, any other questions? All right, well, thank you so much. I hope that was at least entertaining.